Okay, sorry. Decided to break it up into two videos. The previous one was theory, and this one can be problems. So, that's what we previously did. So we're going to find when to use PDF and CDF, basically. And then we're also going to look at mean expected value. Okay, so here's a problem. Here's an example. 72% of all ISZL juniors are in favor of removing the requirement of English classes to graduate. I can't read that anymore. This is what it says. Random sample of 5 members are taken, and the probability that, so we need like 3 people to vote in favor of removing English class from ISLL. Find the probability that 3 are in favor out of the 5, and then the majority vote wins. Okay, fine. Get brains, moron. So, if we were to do this, well, let's do this the slow way. The slow way is 72%. I need to survey 5 people. I need 0.72. I need that to happen 3 times. Great. And I need the complement, the 0.28. I need that to happen twice because there's 5 people, right? And therefore there should be out in front, there should be 5 choose 3. And so we could do that by ourselves with this and say n choose R. This would be 5 choose 3, enter, 10, times 0.72 cubed times 0.28 squared. Cool, okay. 2.29, so this is 0.29. So you have a 29% chance of this happening, right? You definitely can do this by hand, yeah, but you don't need to. This is just kind of the setup, and so you could also do this with your calculator. Hey, I got it right, 293. You could also do this with your and ask your calculator to do this by saying second dister. Nope. Second distribution. I have a probability density function. I want to find exactly 3. So not CDF, PDF, precisely 3. So trials, I got 5 people that I'm testing. Success is 0.72, and I need 3 people to be successful. Paste, boom, there's a 0.29. Cool. So that's how you can use it. All right. So that's PDF. If you were doing the same thing, and you said, let's just modify it a little bit, find the probability that 3 or more, right? Because if I want this bill to pass that says Nick's English class, more time for math and science, I probably shouldn't say that. 3's cool, 4's cool, 5's cool. So you could either do this 3 times and say this and this is good. This is good. So this would be the probability of 3 people saying yes. This would be the probability of 4 people saying yes. And this would be the probability of 5 people saying yes, right? Everybody says yes, nobody says no. 4 people say yes, 1 person says no, and changes the denominator. And then we would find different values here, and then I'm making stuff up, 0.02, 0.01, totally making that up, right? You'd add those together, and that would be the CDF. If we were going to CDF this, I want 3 or more. That means I want not none, not 1, not 2. So you could go, I think the way to run this would be on your calculator, dister, CDF, trials, 5 people, probability of success, 0.72, and I'm going to put in 2 for the value, because I want CDF to calculate. CDF calculates from 0 up to whatever number you put in. So if you want 3 or more, I'm going to first find out the probability of none, 1, or 2 people saying yes. So I put in 2. and then say 1 minus that answer. And this is the probability of 0, 1, or 2. And I want the probability of 3, 4, or 5. So you say 1 minus the answer is the 0.86. Cool. And we could totally you could totally try that with this and see that, punch this into your calculator or find the PDF of the same things and then add those together and you should get that same value. Okay, I guess we probably should have done that problem in the previous video. This is the second part is about mean and standard deviation, and so switch gears a little bit and we'll go for this. Okay, so what's the probability of you've got dice a die? What's the probability of rolling a 4? It's a sixth, right? So the probability of rolling a 4, probability of a 4 is 1/6. If you rolled 6 times and the probability gods are good to you, how many 4s do you expect? Well, if everything goes well in life, you would get a 1, a 2, a 3, a 4, a 5, and a 6 in 6 rolls. So you'd get a 4 once. Therefore, if you rolled 12 times, you would expect that you'd get each number twice, right? If you rolled 6 and the probability gods were good to you, you'd get every number once. 12 times is double it, so you'd get every number twice. So you'd get a 4 2 times. 60, you would expect that there would be 10 sets, I think 10 times, right? And so you get every number 10 times. And what you're really doing is taking the probability and multiplying by the number of trials. So the probability here was 1/6 of the time I'm getting what I want, a 4. And I'm trying that 12 times. 1/6 times 12 is 2. Same thing here. 1/6 of the time I'm getting what I want. And I'm trying that 60 times. Oh, 10. And same thing. If the probability times the number of trials is going to give you how many you should expect if you're gambling, right? So this will give you our expected value. Another name for the expected value is the mean, and they use this little, it's like a lowercase m, hence the kitty, meow. I wish I could roll again, but I'm not. This symbol is the Greek lowercase m, mu, and it's the number of trials times the probability of each one. Cool? So let's use it. Here's the mew. I don't know. So we want to say that the average value, mu, is the expected value, is the number of trials times the probability of each trial. There's also some formulas in your formula booklet about variance, but not standard deviation. This equation, well, this is this equation for standard deviation, about the number of trials and the probability of each. And here's the derivation thereof. It's there. You can zoom in if you want. That's a full page. And there's some more derivation there, and there's some more derivation there. So go ahead and memorize that for me, please. How it's derived specifically is not that important to us. They want you to be able to use it, and the standard deviation and the variance are connected. One's the square root of the other. So if you take the variance is the standard deviation squared, cancels out the root, and you're just left with this inner bit, which is quoted to you in your formula booklet right there. Sometimes they'll ask you to use it, but mostly they're asking you to monkey math and not actually understand it because they don't, the derivation's too complex for us to care about at this moment. So let's try to use it. Okay. Here's a problem, right? 5% of iPhone batteries are defective and will explode in your pocket. A random sample of 80 batteries are taken with replacement. Find the mean and the standard deviation. Okay, so here's our equations that we can use. We know n is the 80 and the probability is 5%, so 1 out of 20. So find the mean. Well, the mean is the number of that we should expect to be defective out of the 80. So n is your 80 and p is the probability of each. So a 20th of 80 is 4. So 4 of them should be defective. Now that we know, let's see, we just use n and p. So we're just going to throw n and p into the standard deviation formula, and we can find did they give us, they're looking for standard deviation. So here's the variance. We'd throw that in there and we'd square it. Because we don't have this equation, we're given the variance. And so you'd throw it in variance. You'd say 80 times 1/20th, which is 4, times 1 minus p. So this would be, so you would say this is 4 times 1 minus p. Probability is 1 out of 20, so this would be 19 out of 20. So the variance would be that value, 19 out of 20 times 4. So this is 3.8. Because that's the variance and we're looking for the standard deviation, we have to take the square root of it. So you got to go square root of that answer. So once you root that, so standard deviation is going to be the root of 3.8. It's a stupid trick that the IB likes to throw at you. We get their same answer, kind of in a different way, because we're not quoted with this, we're quoted with this, which is annoying. So you need to know that you take the variance and you root it to get the standard deviation, or you take the standard deviation and you take the square to get variance. Okay, all right. I think that's it. There's some practice problems in your booklet, and we'll see you later on. I'm going to do one more problem with you now just so you see it. If you want to see it, it's an IB question, but I think you probably have enough to go rock and roll on your next part. Okay, so bye, or here's another one if you don't like life. So there's a box with 240 eggs, and there's probability that an egg is brown is 0.05. Find the expected number of brown eggs. Well, the expected number of brown eggs is just the number that you're going to use and the probability of what you want to happen. So this should be just 240 times 0.05. Sorry, that's so small. Just 12. So it's 240 times 0.05 is 12. Find the probability that there are 15 brown eggs. This is exactly 15. So this sounds like PDF to me, right? Precisely 15 eggs. Well, I would run it like this. Let's show you on the calculator. I'd use second distribution, and I want precisely a certain number of eggs. There's 240 eggs, so 240 is my trials. The p-value is 0.05, and the x-value, I want exactly 15 brown eggs. Boom, boom, boom. We got the 0.073 that I think is hiding in here. Again, sorry, it's so small. 0.073. Got it. Okay. Find the probability that there are at least 10 eggs, brown eggs. Okay, so I want 10 or more, right? If somebody's like, I love brown eggs, they want 10 or more. So they want 10, 11, 12, 13, 55 brown eggs is fine, and 106 brown eggs is fine, and 109 brown eggs is fine, and 230 brown eggs is fine. What I don't want is 0 brown eggs, 1, 2, 3, 4, 5, 6, 7, 8, or 9 brown eggs. Right? So to find that, we would have to say, let's find the probability, let's say, so the probability of at least 10 is going to be equal to 1 minus the probability of 0 to 9 brown eggs. That make sense? So let's find the probability of 0 to 9 by using binomial CDF, second distribution, binomial CDF. Trials is 240, and probability is still the same for each, 0.05. The value I want is 9, because I want it to count all the probabilities from 0 eggs, 0 brown eggs, 1 brown egg, 2 brown, all the way up to 9, and then stop. because then the rest is 10, 11, 12, up to 240. So this is 23.5%, 0.235. Right, so then you go 1 minus 0.235, and you get 0.765, which I think is, wow, way to write super small, Gorkevich. Yeah, great. Cool, hope that helps.